Okie dokie. So I get a lot of requests for turning stuff in late or what have you, and or you know, like, can I leave lab early today or whatever. And just a reminder that all that is written into the syllabus. It's all written into the syllabus, that there's a certain number of times you can leave lab early. There's a certain number of times you can turn a lab in late labs, unless you have a reason or have a small daily penalty, etc. But all late labs, I think the syllabus says you can only turn one in late. But anyway, so okay, I didn't remember exactly what it says. But anyway, so good. All right. So, and last week I felt the need to email you because there were so many people who left lab early, just to remind you that there's a policy about that too. You're absolutely allowed to do that, but only a certain number of times. Okay. So we're talking about timer circuits, and last week we were talking about this op-amp circuit at some point. And I said I would come back to it when we get to timer circuits. That's the last part of today's lab. Before I get into this, any questions, comments? I don't know. I think so much that we do in this class it's just really cool. It's really kind of neat, and it's kind of neat the way this works. Today we're just going to talk about timer circuits. We're going to talk about the basic timer circuit that you can build with an op-amp, and then the timer chip that we're actually going to use, and the way it works. It's kind of cool, and it's got just so many things you can do with a timer circuit. Because what we mean by a timer circuit is a function that changes with time in a regular sense, right? So like a frequency generator. That's what I mean by a timer circuit. A frequency generator. It's got a wave that repeats itself every so often, and you can make a clock out of it, or you can play it through a speaker and you can make a sound out of it, or you can do all kinds of other stuff too with timer circuits. So who remembers the basic idea behind, so what is an op-amp in general? What is an op-amp? A bald op-amp, what does it do? Increase voltage.
It's a machine that tries to equalize the inputs.
That's just a function that it has in it in order to make the output, whatever the output is. What is the purpose of an op-amp? It amplifies signals, right? It amplifies signals. And what is the output of this op-amp going to be if I have inputs on these two inputs?
It depends on the amp.
Depends on what?
The op-amp.
Nope. What's the output of this op-amp going to be? Right? Okay, I can say V in plus. I can give you names. V in minus and V out. This is such a basic and important thing. If you don't know it, you should know it. What's that?
The gain times B plus minus B.
Yeah, the output is a gain times the difference between the inputs. That's the basic way op-amps work. The output is some gain times the difference between the inputs. And then, V in plus minus V in minus. So it's some difference between the inputs. Okay, it's important to understand that, well, because that's what an op-amp does. But it's important to understand that to understand what this circuit does. So, and what is the gain for a bald-faced, unfed back op-amp? What? Infinity. So as large as it possibly can. It's just going to give as large a possible signal times the difference between the input signals. Of course, as large as possible means that it doesn't matter what the difference is. It's just going to give the largest possible signal if we do that. And so remember that this is actually what's called a comparator, because Because if Vn plus is less than Vn minus, then it's going to give you the largest possible negative signal, because it's going to be negative times infinity. So it's either going to be positive infinity if this is bigger, or negative infinity if this is bigger. Infinity being the largest amount of output it can give you. Okay. So one of the things that we can do with that is we can take that output, whatever that output is, which is not really infinity, but if we have a 12-volt power supply supplying our op amp, maybe the output is plus or minus 12 volts. If I take that output and I feed it back to a, what was this called again? Voltage divider. I truly couldn't remember what it was called. I wasn't just testing you, and I'm glad you remembered. A voltage divider. So if that's 12 volts out, and let's just say these two resistors are equal to each other. Yeah, so then it's 6 volts. Yeah. So then it's 6 volts being fed in. It ends up being 6 volts being fed in. Yeah, that's important. Okay, so now what I'm going to do, and just keep that in mind. So what's being fed in is less than what's coming out. Okay. So now what I'm going to do is I'm going to put an RC circuit on the other side. Let me just finish that thought. Yeah, so if this is 6 volts in, then now whatever's going in here, if it's bigger, so if the output max is 12 volts and this is 6 volts going in, then whatever's being fed in here, when it's less than 6 volts, output is going to be plus. When it's less than 6 volts, output's going to be minus. When it's more than 6 volts, output's going to be plus. Okay. So it just gives us something to compare it to. We can change these resistors so we have a different value to compare it, the other leg to. But now on the other leg, what I'm going to do, let me just extend it out here so I can draw an RC circuit. I'm going to put an RC circuit on it. Okay. Don't worry about the op amp for a second. Just look at the RC circuit. Whoops. So I'm going to take the output.
Would it be the same ground?
Always. Grounds are, that's a good question. I'm just looking at everybody. Grounds are always the same ground, by definition. It's a good question, it's an important question, and that's why you got to make sure to plug all your grounds in the same place, always. Otherwise, you might screw something majorly up. Okay, so let me take that 12 volts, and I'm basically just charging an RC circuit. Forget the op amp. I'm just attaching some kind of power supply and charging an RC circuit. Right? An RC circuit is a resistor and a capacitor in series. Put a voltage on that, and what you're actually doing is you're charging the capacitor. I guess that's a damage to the. Oh man! Somebody damaging my whiteboard. Those are actually chips out of the whiteboard. It was probably me. Yeah. If you're ever in my office, look at my whiteboard. There's a nice big indent in my whiteboard. I probably told some of you this before. When I was a much younger person and I had a higher temper, I punched my whiteboard. There was a nice dent. I wouldn't do that these days. I'd just break my hand if I tried to do that these days. Okay, so forget about the op amp. 12 volts charging an RC circuit. What that does is it charges the capacitor, right? And the charging capacitor, if this is V out, the capacitor charge, VC, we're going to call that VC, the capacitor, I'm sorry, the capacitor voltage, not capacitor. It looks like this, right? The capacitor will charge according to, and it'll go up to a maximum of V out. Okay, it's just a RC circuit where the capacitor will charge. But no, this is, I don't know. I think it's fun, but maybe you just think it's stupid. I mean it's just it's a timer circuit, because what happens is that when the capacitor starts to charge, what's the input to the op amp? When the capacitor just starts to charge, what's the input to the op amp? 0, and it's less than this value, right? And so what's the output of the op amp going to be? Negative. And so the capacitor will actually charge, I sort of had this backwards because the capacitor will charge negatively, it doesn't matter. But what happens, will charge negatively? I want to start with a positive output. Hold on a second, sorry. How do I reverse it? What I really want the capacitor to be doing is to be going. So what happens when? Oh wait, shoot.
Just change the +6 volts to -6 volts.
Yeah.
I get it.
Yeah. The point is that when this voltage crosses that voltage, it's going to change whether charging or discharging. Right. So what happens? And that's what I feel like I have a negative sign wrong. I mean, you guys both gave me. Or you gave me a solution. But yeah, let's. What happens is that when. Let me just think a second. Let's just, for the sake of argument, let's. I feel like I have something backwards. Let me just make sure. VC is greater than Vref. When use V out to charge it. When VC is greater than Vref, V out state changes. New Vref and cap discharges. When VC is greater than Vref, state changes. Okay, so let's just assume, right, oh, duh. All I have to do is make this the negative input and that the positive input. Sorry, yeah. So when this is, and that means when this is 0 and this is 6 volts, the output is positive 12 volts. That's what I want it to be, yeah. The output is positive 12 volts. So now this charges, right, but it charges up to, if it was left to charge, it would charge up to 12 volts. But what happens when this gets to above 6 volts?
Then it switches to negative.
Then it switches to a negative output. And so it discharges the capacitor. And and then when the capacitor discharges and goes below 6 volts, so it starts discharging. When the capacitor discharges and goes below 6 volts, then the output changes to a positive, and it does that, and it starts to charge again. So what happens is the capacitor charges and discharges.
Is that VC over?
That we're graphing VC, yeah. We're graphing VC. So that creates a timer circuit. It is a timer circuit. So the voltage on the capacitor looks like it oscillates up and down. What does the output voltage look like? Yeah. It just goes, well, output high and low. High and low, yeah. So the output voltage is a square wave, where this is high and that's low. High and low really is plus 12 and minus 12, if this has a plus 12 and minus 12. But the output looks like a square wave, and the input looks like a, what do we call that again? Shark fin wave. Yeah, the VC looks like a shark fin wave. So that's a timer circuit. That's how we create a timer circuit. Okay, so now, and I might have glossed over 1 or 2 points, especially because I thought I screwed up in minus sign at first. So now, what we're going to do is we're going to take this and we're going to turn it into what's called a timer chip. So you might say, okay, so this is how we create a timer, but what if I want a more controllable timer? And what if I want a timer that reacts a little bit more quickly? One of the things that, I think we might have left off the concept of slew rate. We did not talk about slew rate. Let me talk about slew rate real quick. Actually, this is the place to talk about slew rate. When I asked what does the output look like, and Leif said 0 or 1, he meant that, it's gonna, when this is smaller than this, the output's positive. When this is bigger than this, the output's negative. So it's gonna go from positive to negative to positive to negative, whatever high and low are, right? Whatever those top value and bottom value are. But how does it get there? How does it go from here to here? How does it go from, again, plus 12 volts to minus 12 volts, or plus 12 volts to 0, whatever that output is. How does it get there? Does it just automatically change? No, it's a real signal, right? So it's actually got to, the output has actually got to change. It's not instantaneous. It's a real physical thing. It's electrons moving. So it takes time to change. So there is some time. So even though I meant to draw that like a square wave, I drew it like what really happens, which is that there's some time for it to change, right? And ideally, in a square wave, what's delta t? 0. Yeah, we want that time to be 0. This is slew rate, how fast it changes. Slew rate is how fast the signal can change. So actually, it would be delta V over delta T would be slew rate, right? How fast it can change in particular to a different voltage. Delta V over delta T. And ideally, for a good timer, we want slew rate to be, what do we want slew rate to be for an ideal timer? What? Sorry?
Well, big.
Is it 0 or is it infinity?
Well, 0 wouldn't be changing.
Yeah, okay, yeah. Infinity. I think we want it to be big, yeah. I think we want, ideally, slew rate to be infinity. That the output just changes to what we want it to instantaneously. Oh, I wrote 0. Add another 0. Yeah. That ideally we want the output to be to change infinitely fast. So slew rate is 0. So for a typical op amp, what is the number of those op amp? What do we call it? It's a 394 or 261 or 741. 741. For a typical 741 op amp, you can look up the slew rate. It's just it's a stat. You can look up the slew rate. And the 741 op amp is probably not meant to be a timer. It's just a basic op amp that gives you a differential output given the input. It's not meant to be a timer. So then you might say, okay, so there are certain things about this timer I'd like to improve. I'd like to improve the slew rate. I'd like it to be more controllable. Maybe that's it. Controllable meaning like, what about the high versus low, how long it's high versus how long it's low. That's something that we might be interested in. We'll talk about that in a second. It's called
PWM wave?
I'm blanking on the name. Oh shoot. I have it in here. Oh, I just missed the page. Duty cycle. Yeah. The duty cycle, not duty cycle. Duty cycle is how long it's high versus how long it's low. And things like that. So what we can do, just like what you'll find in electronics, so we gloss over a lot of this, is we say, oh, we can improve this circuit by adding amplifiers and resistors and capacitors, and then we just have a whole new circuit. And we have what's called a timer chip. So what we're going to do, instead of pulling out a 741 and adding 3 resistors and capacitor, we're going to pull out a 555, which is a timer chip. Okay? And the timer chip basically works like this, but it's got additional components inside of it that allow it to slew more quickly and then allow it to be flexible in other ways. Okay, but this is the basis of a timer chip. Okay, so what we're going to use is the 555, and you can look it up and see that the 555 probably has a significantly higher slew rate than the 741. But the 555 is made to be a timer chip, so it's got different inputs. Timer chips, for whatever reason, are often drawn as squares, but they're not square, they just look like a chip. Same thing like a 741, right? They just have, the 741s I think are 6 inputs, is that right? Were there 3 on either side, or was it 4 on either side? 4? Oh, so it's 8 input? Okay, so, and the timer chip is also an 8 input, so they're gonna look the same. Okay, so the basic timer chip is a 555 IC. 555 integrated circuit, and that's just the number, that's just the product number. And by the way, I've been teaching this class for almost 20 years, And there become some very standard chips, like the 555 and the 741. But over time, sometimes they become obsolete because somebody makes a better chip. And you've probably seen that in the lab where I have a number on a chip, which I say don't use that anymore, use something else. Sometimes it's because they're not made anymore because they just come up with a better chip. But it's because somebody designed the insides. It's a black box for us, right? Okay. So the 555. We've got a ground pin, an output pin, a control pin, a voltage. VCC generally means the voltage that we're feeding it. CC actually mean? I can't remember what CC actually means. A reset pin, which I think we don't use the reset or control pins. And the three important pins are the discharge, the trigger, and the threshold. Okay, discharge, trigger, and threshold.
Those last two are in the wrong order.
Not for me.
Okay. As per this diagram, they're in the wrong order.
Oh, are they? Okay. Okay. And actually, yeah, actually, you're right. For the sake of the circuit I'm about to do, it doesn't matter which way the trigger and threshold are. You're absolutely right. You're absolutely right. Okay. But yeah, I'll leave it the way I have it. Okay. And for the 555s, these are actually pin 1, 2, 3, 4. Again, you could just look this up, right? I don't need to tell you this. You can look this up and the pin out. So control must be 5, right? 1, 2, 3, 4, 5. Yeah, 5 is missing. Okay. Okay. For the 555, those are the pins. All right. So we're going to draw what's called the classic astable vibrator. So this is the 555 AC, and we are going to draw the classic astable vibrator, or if you prefer, oscillator. Because I've told you this before, when you Google physics equipment vibrator, you don't get what you're looking for. It's so frustrating. Okay. So we've got a capacitor, ground, voltage. This is attached to VCC and reset. Oh, I guess we do use the reset pin. Okay. Discharge, trigger, threshold, resistor. Okay. So, what you are going to do when you set up this circuit is you're going to plug in the 555, and you are simply going to make 2 resistors and a capacitor and a power supply. All right, just keeping in mind, this is the power supply that gives us the input, right? We also have, oh, wait a second. Oh no, we don't have other power supplies in this. Like I say, you also have the power you don't. This, I guess, powers the whole circuit. We don't have additional pins for more power. Huh, okay, my mistake. All right, so I guess we only have one power supply for a timer chip. I don't know why that just doesn't. I don't remember that. Okay, so unlike the op amp where you had to have 2 power supplies plus your inputs, up to 4 power supplies, we only have 1 power supply here. Okay, so so here's how the timer chip works, and the question you may have as we go along is, why does the timer chip work like this? Well, what's the answer?
Smart people made it that way.
Yeah, exactly. Smart people made it that way. Yeah. We're not explaining why it works like this, so we're just saying smart people made it that way. Exactly. Okay, so if you imagine turning on VCC, so we just turn on the input power. What happens is the capacitor, which we're just going to call the voltage across the capacitor starts to charge up. Right, so initially VC equals 0. The capacitor has no voltage across it. It will charge up through the 2 resistors. So initially, the initial conditions are going to be VC equals 0. Discharge is open circuit. What does that mean? Say again. Well, it does mean no current, absolutely. It means, yeah, I guess that's the biggest thing, is it pulls no current, and it doesn't allow any current to go in that direction. It means it's as if it's not there. But you're absolutely right, that's what it means. It means no current. It's as if it's not there. And the trigger and the threshold are detecting what's going on. That's what the trigger and threshold are. They're detecting what's going on, and they're going to make something happen. Okay, so V trig and V threshold initially are going to be equal to 0, and the concept behind V trigger is it's always, but the way sorry, I said and I didn't write classic. This circuit is the classic astable vibrator. In the classic astable vibrator, VC is always equal to V trig, is always equal to V threshold. Right? The voltage across the capacitor is equal to those two. It's just attached to those two pins. And these are the two pins that are trying to figure out what's going on. And so that's initially, and then what happens as time flows, as time goes on, beyond Vt equals 0, Vc starts to charge, right? Vc starts to charge. And as Vc starts to charge, the trigger and the threshold are measuring the voltage on the capacitor. And what the trigger and the threshold do is that as the trigger is less than 1/3 VCC, it keeps discharge open as in open circuit, and makes output high. Meaning the output is just the maximum output. Okay. So it starts at 0, the discharge is open, output is high. When the threshold is greater than, 2/3 VCC, it makes the discharge go to ground and V out low. Okay. So, what happens? Capacitor is charging up, it starts from 0, output is high. Capacitor is charging up, it's going up towards 1/3 VCC, output is high. We're above 1/3 VCC, nothing happens. Capacitor is charging up, output is high. But what happens when the capacitor charges to 2/3 VCC? Say again? V out goes low, and now discharge goes to ground. So the capacitor, which is, we can look at the capacitor charging, and if this is VCC, when the capacitor gets to 2/3 of VCC, then the output goes low and discharge goes to ground. So this is what's going to happen to the capacitor at first. At 2/3 VCC, output goes low. So we can look at, along with that, what the output looks like. And I've drawn this in a corner. That's stupid. Let's just draw it up here. V out. What did we say it was? It was high. High until we get to 2/3 VCC. And then it goes low. And again, we're assuming an infinite slew rate there, but whatever. Okay, so now what happens? this is now, so now we're at 2/3, we're at where the capacitor is charged to 2/3 of this value. Now what happens is this pin goes to ground. So what happens to the capacitor if this pin goes to ground? Again, these two pins are only detecting things. They don't do anything. We can just pretend they're not there. So what happens when this pin goes to ground?
It starts discharging.
Capacitor starts discharging to ground. Yeah, it's as if when you have a ground, when you stick a ground in the middle of the circuit, the rest of the circuit might as well not be there, right? So the capacitor starts to discharge to ground. So the capacitor is going to start to discharge, and V out goes low, right? What I want you to notice is that when the capacitor is charging, it's charging through what resistance? What resistance is the capacitor charging through? What resistance does the current have to move through in order to charge the capacitor?
RB and
RA plus RB, right? The total resistance of the circuit is RA plus RB when it's charging. And when it's discharging, what's the total resistance of the circuit? Just RB. Yeah. Yeah. So it's going to discharge and charge at a different rate. Unless, so it's going to charge at a different rate than it discharges unless what? How can we make, I got to remind you, I've got to remind you that the charging rate and discharging rate of a capacitor has to do with the constant called R times C, the total resistance of the circuit times the capacitance of the circuit. So it's charging at a rate which is proportional to RA plus RB, and it's discharging at a rate which is just proportional to RB. So how would we make it charge and discharge at the same rate?
RB is huge, RB is small.
Yeah, RB a lot bigger than RA, or RA is equal to 0. Yes, either of those works. RB a lot bigger than RA, or RA equals 0. So we could just short the RA, and then it would charge and discharge at the same rate. Yeah. Okay. Okay. So what it's going to do is now we're at where we've grounded, the discharge out is low, and we discharge until what? We discharge until what?
It goes below 1/3 ECC.
Until the capacitor charge goes below 1/3. So I didn't quite, sorry. Sorry if I messed up your notes. I had to discharge to, that's where it stopped discharging, 1/3. And when I say 1/3, 2/3 here, I mean 1/3 and 2/3 of VCC. 1/3, 2/3. So then it's going to start charging again until it gets to 2/3 VCC. It's going to discharge until it gets to 1/3, charge, discharge. This is going to be high, low, high, low. Okay.
So it has even less of a slew rate than the initial one?
The slew rate is different only because the circuit is made to have a different slew rate. It's nothing to do with how we set it up. Yeah. Because the slew rate doesn't have to do with, so just be careful, I want to make sure. The slew rate doesn't have anything to do with this or this. It has to do with just what happens right here. Right? The slew rate has to do with what happens right at that instant. What happens at that instant. And we're assuming what happens at that instant happens instantaneously, which is assuming an infinite slew rate. Okay. So the reason why this is now this is a better timer because it's just made to have a better slew rate. It's also a controllable timer because, like I said, we're charging it through RA and RB and discharging it through RB. So we can now vary the amount of time it takes to discharge versus the amount of time it takes to charge. Okay. So, and by the way, this part right here, we never see again, right? That's just the first time we plug it in. After that, it just goes do, 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 right? Okay. Okay, so I drew this as sort of a symmetric charging discharging, but it's not because these, how long it's charging, how long it's discharging is going to depend on RA and RB. So what I'm going to do is skip the derivation of the RC circuit, which I would normally do at this point, but I think I won't, and just remind you that the time constant for an RC circuit is RC. For RC circuit is RC. Oh my gosh. Yeah. Sorry. I'm like, wait. No, maybe I need to. Sorry. I don't know why basic things are not coming back to my memory here. Let me be careful here. Yeah, the time constant. Okay. Time constant of an RC circuit is RC. And what is that? Does anybody remember what it means? Time constant is the capital tau. Does anybody remember? That has nothing to do with classification for that circuit. The time constant for charging and discharging is RC. That comes from a derivation of the differential equation. When we look at that V minus IR minus Q. I always forget. C is Q over V, so Q equals CV. V equals Q over C. Yeah, that's what Q over C. So Kirchhoff's rule for an RC circuit would say that V minus IR minus Q over C equals 0. That's Kirchhoff's law. And then we solve that differential equation. Why is it a differential equation? I equals Q over T. Yeah, so it's a differential equation. It's dQ dt, really. Yeah. So it's a differential equation. And what we find is that the differential equation gives us this shape, right? V versus T, right? That's what tells us it charges like that and discharges like that. So what does this time constant represent? Again, I haven't done the full derivation, but that time constant comes out of the differential equation. What does that time constant represent physically?
The time it takes for the capacitor to charge up.
It represents something to do with the time it takes for the capacitor to charge and or discharge. Absolutely.
Over seconds, right? That's the units of tau?
No. Tau is actually seconds. RC is actually seconds. And the reason why you're thinking 1 over is because it comes in the bottom of it comes in the denominator of fraction. When you look at the equation, V equals V0 times 1 minus e to the minus t over RC. That's the actual charging equation. And the actual discharging equation, V equals V0 e to the minus t over RC. Whoops, we don't need parentheses there. So that's what we end up getting as a result of the differential equation, is the charging and discharging. And that RC actually has units of time because it's T over RC, so it must have, that ratio must be unitless. So it has units of time. Yeah, I always find that fascinating. Ohms times farads equals seconds. I think that's like, why? I've never quite understood conceptually why.
Well, at a certain point, we have to give up on that. Like,
Yeah.
meters per second, I get that one.
Yeah. But anyway, yeah. So it's kind of funny. So what Jackson said is that tau is just a measure of how long it takes to charge and discharge. It's not exactly how long it takes to charge and discharge, right? Because tau, this is tau right here, RC, right? That's tau. Because when t equals tau, then it's either 1/3 charged or 2/3 charged, right? It's 1 minus 1 over e. 1 over e is about 1/3. Yeah, it's about 1/3. So it's either 1/3 charged or 2/3 discharged at t equals RC. Do you see that? At t equals RC, it's either 1/3 charged or 2/3 discharged. So it just gives us a measure of how long it takes to charge and discharge. How long does it actually, this is not an important question for the timer. How long does it actually take to fully charge a capacitor?
No.
Well, right. Ideally, it takes an infinite amount of time. In reality, it doesn't take very long at all. So you're both right. But it actually takes an infinite amount of time to charge because this is an asymptote, right? This is an asymptote. It actually, in most cases, for most RC circuits, it's microseconds or milliseconds, but it does asymptote to its maximum value. So it's infinite. So we can't really talk about how long it takes to charge a circuit, but we can talk about the time constant for the circuit, which is a measure of how long. Okay? Okay. So what I will point out is if you remember any of that, then this will be obvious. If you don't remember any of that, this will just be fact. Is that therefore or I mean, I can plug in for charging, for the charging of the capacitor, that's this part here, charging. It's charging through RA and RB, so T charging is RA plus RB times C, and tau discharging is equal to just RB times C. So those are the time constants for charging and discharging. And did I need to? I'm gonna come back to that in a second. No, I don't. I need to explain that. Shoot, I need to explain that. Yeah. Okay. So I'm going to erase this. You still have it in your notes. I need more space. This is the last part. What I want to do is figure out my V out, which was high, low, and these are not necessarily high and low for the same amount of time. I'm going to call this delta T charging, that's when it's charging, and this is delta T when it's discharging, which is different than tau. Tau is the characteristic time, the actual amount of time. So, for a charging cycle, forget the very first cycle. I drew this like it was the first cycle, but forget the very first cycle because that was different than all the rest. For the normal charging cycle, the capacitor goes from what voltage to what voltage during that charging cycle? What was the capacitor's lowest voltage and the capacitor's highest voltage?
1/3 VC is the lowest, and 2/3 VC is the highest.
Yes. While charging, the capacitor goes from 1/3 VCC to 2/3 VCC. And when discharging? Somebody else.
2/3.
Yeah, thank you. While discharging, VC goes from 2/3 VCC to 1/3 VCC. Okay. So we can then say, oh, okay, so whoops, here's VC, this is the voltage across the capacitor for charging and discharging. So these equations, I did sort of say, I'm just gonna throw those equations up, you don't have to worry about them, but I realized in order to do this derivation, you gotta understand them, or you just take the derivation as given. So let me just rewrite those. VC equals, I wrote V0, but the maximum voltage, VCC, actually, I gotta be careful here. All right. No, that's correct. We're charging with VCC. Times 1 minus e to the minus t over. Okay, so this is the charging cycle. When it's charging, this constant is RA plus RB times C. And when it's discharging, e to the minus t over RA times C. RB, not RA. RB. Okay. So what I want to do is I want to know how long does this take? In other words, what is delta T charging? And then I want to ask the same thing for that. How do I figure that out? How do I figure out this? I'm asking you a math question, really, more than a physics question. I want to know how long it takes for VC to go from 1/3 VCC to 2/3 VCC. It's not a hard, if you really think about it, it's not a very difficult question. It may be for you, but it shouldn't be. Sorry, so let's just try somebody else. I want to give people time, a second to think about this. So I want to answer the question, how long, what is this delta T charge? How long does it take? How long is it going to be high for? It's going to be high for the amount of time it takes to go from 1/3 VCC to 2/3 VCC. How can I use this equation, which is the charging equation, charging to figure out that amount of time.
Substitute in the values and then solve for the T on top?
Yeah, exactly. Substitute in the values of 1/3 VCC and 2/3 VCC and solve for T. And then find the difference between them. Yeah, so we're gonna say, therefore 1/3 VCC equals VCC times 1 minus E, 1 minus E to the minus T, we'll call that T initial.
Wouldn't that, if it's charged, it wouldn't be 2/3 VCC? Charging from 1/3 to 2/3. No, starting at 1/3, finishing at 2/3. It doesn't matter. If I'm wrong, then it's just gonna be a minus sign. Doesn't matter. Delta T is still gonna be delta T. And then 2/3 VCC equals VCC times 1 minus E to the minus T final over RA plus RBC, and delta T charging equals T final minus T initial. Just solve. It's easy. It's easy. You can all solve for that. And what you find is that delta T, the amount of time it takes to charge, is equal to RA plus RB. Make sure, sorry, 0.69. There's a 0.69 because you got a natural log of something. Equals 0.69 times RA plus RB times C. This is what we were looking for. The amount of time it takes to charge. How long does it take to discharge? You should be able to tell me without doing any more math. But
Without one of the resistors.
right. Which one again? RB. So that tells us what how long this one is and how long that one is, how long that one is and how long that one is. Okay. So therefore, everybody should be able to answer this question. So everybody think about it before anybody answers. What is the total period? What is the period of one full oscillation, right? Period of one full oscillation, period of one full oscillation. Everybody think about it. What's the total period of one full oscillation? Simple question, right? Who thinks it's an easy answer and they can tell me what the period for one full oscillation is? Nobody else? What is the period? All right, go ahead. Go, wait, who is? Tyreek, were you gonna say something?
The addition of both of them.
Yeah, exactly. Yeah, that's what I mean. It was trivial, right? It was trivial. It's just the sum of the two. It's the sum of the two. So therefore, you are absolutely right. Thank you. No trick there. So the period is delta T charge plus delta T discharge, which is 0.69 times RA plus 2RB times C. So the period of oscillation of this astable vibrator is 0.69 RA plus 2RB times C. So you can see how you can now set the period of oscillation. You can also set how much this is versus this is. The duty cycle is defined as, it's either high over low or low over high. The amount of time, the fraction of time the output is high. Oh, the fraction of the total time, it's not high over low or low over high. Fraction of the total time the output is high. Fraction of the total time the output is high. That's the definition of duty cycle?
So we try to shoot for 1/2.
Nope. But I know what you're getting at. But give me a second. Fraction of total time output is high. So it's high for 0.69 RA plus RB C, and the total time is 0.69 RA plus 2 RB C. So the duty cycle DC duty cycle is equal to, we can simplify that, right? That's the duty cycle. So what Jackson just asked is, would we be shooting for a half? Half means that it's high the same amount of time as it's low. Yeah? So he's absolutely right. That may be an application we want. We want it to be high for the same amount of time as it's low. Right? Yeah? I mean, that might be something we want. So if we want it to be, if we want the duty cycle to be a half, DC equals 1/2, so it's high and low, so it's symmetrical. That's what you're getting at. We like symmetry. That's only just one example of a duty cycle. But so if DC is 1/2, therefore what would we, what might you choose for your resistors to make DC equal to 1/2?
RV could be anything, just nothing for RA.
Right. RA equals 0. If RA is 0, then no matter what RB is, you got a duty cycle of 1/2. What, for the classic astable vibrator, what are the ranges of duty cycle? Can you get anything? Oh, sorry. What is the possible range for duty cycle? Duty cycle can be, what's the possible ranges? Not for this, but in general.
Never on, always on.
Right, never on to always on, 0 to 1. Yeah, a duty cycle of 0 means that it's never high. A duty cycle of 1 means it's always high. A duty cycle of 1/2 means it's high half the time, which is, okay, we're gonna make some jokes, right? Dylan, how often are you high? What's your duty cycle?
I have no idea.
I saw you laughing, that's why I picked on you. Yeah. So anyway, yeah, so it's just the fraction of time that you're high. Now you can calculate everybody's duty cycle. And we should correlate that to their grades.
Yeah,
Okay.
then what if you really have to rethink your teaching style?
Oh dear. Okay, so but this actual the classic astable vibrator does not range from 0 to 1. What's the lowest possible duty cycle it can have? 0. It can't have 0. Oh wait, how would you get 0? How would you get a 0 duty cycle? I'm actually going to say you can't have 0. How would you get 0? What would you think?
No R, no B.
Right, no R, no B would give us
But-
0 over 0.
Yeah.
Yeah, so it wouldn't be actually 0. Yeah. Right.
We had like negative resistance.
Yeah, and there's no such thing as negative resistance. You're right. Yeah. So that's a good point. But yeah, so it turns out that the lowest duty cycle you can have, think about this number here, with RAs and RBs being constants, which are 0 or larger. The lowest duty cycle you can have is a half, and you can have a duty cycle of 1. How do you get a duty cycle of 1 out of this?
Make RB 0.
Make RB 0, right. If RB is 0, then it's a duty cycle of 1. So so we can get a half and we get 1, we can get anything in between, but we can't get anything less than a half.
You can
Okay.
turn it off.
You can turn it off. That doesn't count.
So it'd be no resistance when it discharges, so it does it almost instantly.
Yes. Yeah, I think that's a good conceptual point. If RB was 0, there would be no resistance when it discharges, so it would discharge almost instantly, so it'd be almost high all the time. It'd be high, it'd blip low, and then go high. Blip low, then go high. That is a clock, right? That's a clock. You might say, oh, isn't the clock when it's half, duty cycle is half? No, actually a clock is really when it's high all the time, except for, right, it's just counting. 1, 2, 3, 4, right? High, blip, high, blip, high, blip. Right, so that's so a duty cycle of 1 is more like a clock. See what I'm saying? Some of you see what I'm saying. Yeah. Okay, that's it. That's everything. And then the other thing just to recognize, which you already wrote, is that the output is a square wave, or the capacitor's voltage is still a sawtooth wave or a shark fin wave, depending on what shape of wave you want. But they both have the same duty cycle. And that's it. You guys can get to work. Unless you have any questions. Oh, thank you. Thank you, yes.